Welcome back, everybody. So today we are just going to finish up the Chapter 9 lecture note outline packet. So you'll want to make sure you have that open to this page. This is where we left off the last time. So let's go ahead and get started. So we were talking the last time in the last lesson about covalent bonds, which is the sharing of electrons. And we looked at sharing a pair of electrons. So we looked at what are called single covalent bonds. So that was the previous page to this. Now we're going to talk about another type of covalent bond, which is called a double bond or double covalent bond. Now, as you might expect from the name, a double bond consists of two bonds rather than one. So a double bond is really two individual single bonds together. So instead of when we talked about a single bond being the sharing of two electrons, the double bond is the sharing of four electrons. So it's actually two pairs of electrons rather than one pair, like in a single bond. So here's what a single bond looks like. It's a single line that represents two electrons, and a double bond looks like this. It's two lines between atoms, and it's two sets of two electrons, or four electrons total. So to see how this works, let's look at oxygen gas. Oxygen gas consists of two oxygen atoms. So let's start off by just drawing the oxygen atoms and their lone pairs before they're bonded. So oxygen is in group 6, so we should have 6 electrons around oxygen. That's the valence shell. So if I draw them like this, I get two paired up electrons. So I have two sets of pairs, and then I have two electrons that are unpaired. Right? And this is following that rule I showed you in the previous lesson, where when we're drawing the electron dots, we show them singly before we start pairing them, and then we just kind of go around the four sides, drawing in the dots for electrons. So now that we have the electrons drawn, the valence shell electrons drawn for oxygen, let's see how bonding would work. And remember, when we're doing bonding, what we're really trying to show is how these atoms, when they sort of come together, how each of them can have an octet of electrons, so 8 electrons in the valence shell, through the covalent bond, which is the sharing of electrons. Now, you might notice that each of these oxygen atoms needs 2 electrons to have an octet. So if, for instance, this oxygen, if we had an electron here and an electron here, that would be a full shell, and that would be stable. So this oxygen needs 2 electrons, and this oxygen needs 2 electrons. We can achieve that by allowing each oxygen atom to share a pair of electrons. So if we have a sharing going on here and then a sharing going on over here, each of these oxygen atoms could have an octet or a full shell. So let's show that. So if we share the pair of electrons up here and down here, we see that we can have 2 bonds between these oxygen atoms, the sharing of 2 pairs of electrons. So that's a double bond. Now we can show this with the dots like I'm showing here, or we can replace these dots with the normal line representing the sharing of 2 electrons. And if we transform these 4 electrons into lines, that means we would need 2 lines or a double bond between the 2 different oxygen atoms. So that's what I'll draw over here. So notice also that we have 2 different kinds of electrons when we're drawing this. We have bonding electrons. Those are the electrons that are in bonds between atoms. But we also have non-bonding electron pairs. And those are the electrons that aren't bonding. We're going to learn actually that in this lesson, we're going to learn that the shape of a molecule will depend on these 2 things, the number of bonding electrons and the number of non-bonding electrons around an atom. And from that information, we can often determine with a pretty good accuracy the shape of a molecule. Anyhow, before we do that, let's look at another example with carbon dioxide. This molecule also shows double bonding. So carbon dioxide, as the formula shows, has 1 carbon atom. Carbon is in group 4, and it has 2 oxygen atoms, and oxygen is in group 6. So let's put the electrons, the valence electrons, around each of these atoms before we get started figuring out where the bonding is. So we see carbon has 4 valence electrons, and each oxygen has 6. Now if we take a look at carbon, notice that carbon has the need for 4 additional electrons. So an electron here, 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 and over here. Notice oxygen, each oxygen needs 2 electrons to complete its octet. Each oxygen has 2 electrons to share. So if we shared 2 electrons from this oxygen and 2 electrons from this oxygen with carbon, carbon could get an octet, but also oxygen could have an octet. So let's see what that looks like as far as where the bonds are. So we can see a bond happening here where we share an electron from a carbon and an oxygen to have one bond, and then another bond between those as well. And we can do the same thing on the other side. And if we do this, we get 2 bonds on either side of the carbon, a double bond to the oxygen on the left and a double bond to the oxygen on the right. Let's transform this into our line bond drawing structure, where we have the lines representing the bonds. And we see that the carbon here has 4 bonds going out to oxygen, and then each oxygen has 2 non-bonding pairs on it. So the carbon has no non-bonding pairs. All of the electrons are involved in bonds, but the oxygen has non-bonding pairs on it. So that's carbon dioxide, and that's pretty much what we're going to get up to as far as bonding goes. Now, there are also triple bonds. We're not going to be doing that in this class. We'll restrict ourselves to single and double bonds. But just so you know, there are also triple bonds. Now, the next part of this talks a little bit about some little details about covalent bonds. Now, it turns out not all covalent bonds are created equal. And we are going to learn about the 2 major types of covalent bonds, those being polar covalent bonds and the other being nonpolar covalent bonds. So let's look at what that means and how to identify it when you see it. So first, let me describe to you this term electronegativity. Electronegativity is a term we use to describe the way atoms behave when they're bonded with other atoms. Now, some atoms are a lot more sort of greedy for electrons than others, and we say that these are highly electronegative atoms. So an atom with a greater electronegativity is something that's going to take electrons in a bond towards it. We see these are electron rich in the bond. Now, there are atoms, of course, with lower electronegativities, and lower electronegativity in a bond means that atom will have less electrons around it. So we say it's electron poor. An analogy would be like this picture I have drawn here, where we have this little baby, and then there's like a football player, and there's this bond between them, which is represented by this rope. Now, some atoms are like this. Like we have some that are really kind of like electron hogs, like we have on the right over here. That in the bond would be something that was more electron rich. So that's the one with the higher electronegativity. And then with less electronegativity, we get less electrons around that atom. So what we're going to talk about are these bonds, the nonpolar covalent bonds and polar covalent bonds. Nonpolar covalent bonds occur when 2 atoms with similar or equal electronegativities are bonded together. So that would be like if we had the 2 football players here. They had similar electronegativities, or 2 children, for example. Now, that's called a nonpolar covalent bond. On the other end of the spectrum, we have polar covalent bonds. Polar covalent bonds occur when we have 2 atoms that have very different electronegativities, like the one that I've shown here with the little child and the football player. That would be a polar covalent bond because the electrons are not shared equally between the 2 atoms of the bond. One has more than the other, and we call that polar. Okay, so I'm going to actually draw some sort of diagrams showing this, because I don't expect you to draw the football player and the little child. I want to actually show you with sort of generic atoms called A and B, and show you what the bonding would look like in each of these 2 scenarios. So let's take a look at how that works. So first off, let's imagine we had 2 atoms, and they're both called A. Now, atoms A are identical atoms, so of course because they're identical, they'll have the same electronegativity as another. So atoms of the same type have the same properties, and electronegativity is one of those properties. Now, if we imagine these atoms A being bonded together, because they have the same electronegativity, neither one will have more electron density of the bond than another. It's like a game of tug of war where we have equal competitors. So they're pulling on this bond exactly the same. So the electrons are evenly dispersed or equal around them. We don't have more on one side than another. And this is what we call a nonpolar covalent bond. So again, a nonpolar covalent bond is when we have two atoms that have similar or equal electronegativity bonded together. And when that happens, this nonpolar covalent bond that forms has an equal distribution. There's not more of electrons of the bond on one side than another. Again, that's called a nonpolar covalent bond. Now let's talk about what a polar covalent bond is. A polar covalent bond, as I wrote here, occurs when we have two atoms that have different electronegativities. So this is not a good example of that, right? Up here we have atoms that are identical in terms of their electronegativities. Let's imagine a situation where the atoms are not identical. So maybe we're talking about atoms, instead of A and A, we're talking about atoms A and B. So let's draw two atoms, atoms A and atom B, and let's write over here in a little note that says that A and B have different electronegativities. You know, contrast that with the previous example, which A and A had identical electronegativities. So here we have A and B with different electronegativities, and let's just suppose that B has a greater electronegativity than A. So it's more electronegative than A. I'll show you later on the next page how to know which atoms have greater or less electronegativities. But for now, let's just presume that B is greater than A. So if B has more electronegativity than A, that means when A and B are bonded, B would have a greater share of the electron density than A because it is more electronegative. So electrons would be spending more time around B than A. That means we have less electron density around A and more electron density around B. And this is called a polar covalent bond. So one question you might have at this stage is, what effect does this have on actual chemical properties for the molecules being A bonded to A or A bonded to B? Well, when we have a polar covalent bond, the properties of the molecules that have those polar covalent bonds can be very different from the molecules that don't have those. So for example, if we look at the polar covalent bond, because there's more electron density on one side than another, we would expect one side to be slightly more negatively charged than the other, which would be slightly more positively charged. So A over here with less electron density around it would be slightly positive, and this would be slightly negative. And that means it's going to interact with other molecules in a very different way, which we'll learn about. Now, contrast that with a nonpolar covalent bond where we have sort of a symmetrical situation here where the electron density is even on both sides. When that happens, neither side is more positive or more negative than another. And for that reason, this would have very different chemical properties because of the way it also interacts differently with its environment. So we'll learn about those situations here in a minute. Now, we're going to go to the next page where I'm going to show you how you can actually know which atoms have greater electronegativities than others, so that you can predict when you're looking at something, whether you're going to say that's a polar covalent bond or a nonpolar covalent bond, just by looking at it. So let's take a look at the next page. So on the next page, you'll see here I have a graphic of something called the Pauling scale of electronegativities, or the Pauling scale as it's known. And what this is a chart, and I've mapped it here to the periodic table. It's graphically oriented as well, so that you can see the relative electronegativities between atoms of different types. And from this chart, we see there are some numbers that are printed on here. Now, I want to point out first that these numbers, which you'll see, like for example, on potassium, it's 0.9, or on fluorine, it's 4.0. These are numerical values that are supposed to represent relative scale of electronegativities. So higher numbers correlates with higher electronegativity. So they're directly proportional to one another. Lower numbers is a lower electronegativity. Now, this scale, these are approximate values. So we don't often do calculations or anything with these numbers. They're just there to provide a guideline to say, hey, this atom is, say, 20% more electronegative than another. So it's a guideline, and they're not always perfectly accurate. Actually, if you take two atoms together under the right circumstances, you can see the variations in these numbers. Now, we're not gonna take it to that level. We're just gonna be using this as a guideline for us to determine if a bond is polar or nonpolar. Okay, so if we have two atoms of the same electronegativity bonded to each other, we would say that's a nonpolar bond. But if they're different from one another, then that's a polar bond. And some bonds are more polar than others, of course. So that's the Pauling scale of electronegativity. Now, I want to point out probably the most important thing about this chart is rather than the actual numbers themselves, which of course you would have if we had you writing things down, we would give you this list. We're not going to have you memorize it, of course. One thing that's very helpful, though, is the trend on this table. So you'll notice the main thing here is that if you look at the way that these step up, you'll notice that fluorine is the most electronegative element on the periodic table. And you'll notice that pretty easy to see here. The trend is that when we go from left to right, the electronegativity increases. So boron is less electronegative than carbon, and then we go up from there. Now, so that's the trend. Going from left to right, the electronegativity increases. Let's write that down, actually. So one way I've done this before is I go, if you're looking at the periodic table, so you've got this is your periodic table. If you're going in this direction, from left to right, the electronegativity increases. Okay, so that's in the same row. Now that's not to say, like, what if you go like down, right? If you notice, if you go down, like from boron down to aluminum, it decreases. Carbon down to silicon, it decreases. Nitrogen down to phosphorus, it decreases. And then you can see fluorine, chlorine, bromine, iodine, it decreases. So the trend is, if you're going from the top to the bottom, the electronegativity decreases. So we can say, well, the opposite of that is it increases going from the bottom to the top. So this is also an increase in the electronegativity. And sort of everything epicenters at fluorine. That's the greatest electronegativity. So electronegativity increases towards fluorine, which is the most electronegative element on the periodic table. So that's the trend. Now, some of the problems with that is, what if you go diagonally? Like, what if you go like down and to the right, or up and to the left, for example? That's when you can start getting into some little issues where it can be hard to predict. Like if you're just going from left to right or bottom to top, it's fairly easy to predict. But let's take a look at a diagonal relationship real quick. So one of the ones that I always remember is carbon and sulfur. So if we look at carbon and sulfur, if we go from left at carbon up to the row that sulfur is in, oxygen, we're increasing electronegativity, as we would expect. But then we have to go down to get to sulfur. And that means carbon and sulfur have identical electronegativities. So if we had carbon bonded to sulfur, that would be a non-polar covalent bond. But carbon bonded to oxygen would be polar because they have different electronegativities. So that's the basic idea with the Pauling electronegativity scale. Now, I want to give you a few other tools to work with when you're actually, how do you show that a bond is polar or nonpolar, right? How do we actually just show that when we're drawing a structure, for example? Well, there are actually there are two common ways to show polar or nonpolar covalent bonds, and I want to show you both. One of the methods that we use, which I'm showing here in part A, is called the delta method, where what we do is we use this Greek symbol delta, which you can draw. It's kind of like, it looks like a little snake or something. This is one way to draw it, kind of like that. This is called delta. And delta, this is the lowercase delta in Greek. We show little delta to show, this means like partial or a small amount, is when we use this little delta. It's a small difference. And when we show delta with a plus, that means it's partially positive. So this is a small plus. It's not a full positive charge, it's a little bit of a positive charge. And then if we put a little negative sign next to a delta, that means it's a small negative. So the way we use these delta symbols to show a polar bond or a polarized bond, imagine back to the situation I showed on the previous page where we have A bonded to B and B is more electronegative than A. In that case, we had more electron density around B than A. So there's more electrons around B, making it more negatively charged by a little bit than A, which has less electron density and therefore is a little more positive than B. We use the little delta symbols to show that. So notice here I've shown the delta negative around B. That's because B has more electron density around it because it's more electronegative. So if we have a polar bond, we show a delta negative next to the more electronegative atom, and we show a delta positive next to the less electronegative atom. So that's basically how we use these delta symbols. Let's look at an example with carbon tetrafluoride. So I'm going to draw the structure for carbon tetrafluoride, and then we're going to assign delta positives and delta negatives next to the atoms where they belong. So the Lewis dot structure for carbon tetrafluoride just has a single bond between carbon and each of the fluorine atoms, and then we have the lone pair electrons, the non-bonding electron pairs on each of the fluorine that complete the octet for those atoms. So now that we have the Lewis dot structure for carbon tetrafluoride, let's actually take a look at the electronegativity scale, the Pauling electronegativity scale, and see what the electronegativities are for carbon and fluorine so that we can determine which one is more electronegative and which one is less electronegative. So if we notice here, fluorine, of course, is the highest electronegativity. It has a value of 4. And carbon, as I showed you earlier, has a value of 2.5. So actually, let's go back to our drawing down here, and then let's write down these values right next to each of the atoms so that we can see which one is more electronegative and which one is less electronegative before we put in our delta signs. So I'm just going to mark down 4.0 for each of the fluorine atoms and then 2.5 for the carbon atom. Now I'm going to redraw this with the delta signs in place. So we see that fluorine is more electronegative than carbon. So that would mean that fluorine would get the delta negative and carbon would get the delta positive. And this is just repeated over the 4 different bonds. So essentially we have 4 different delta negative fluorine atoms, and then we have this one delta positive carbon. Another method we have for denoting polar bonds is the arrow method, which I have here in part B. What we do is we use an arrow that points towards the more electronegative atom of a polar bond. So if we had A and B bonded together, and again, B is more electronegative than A, we would draw an arrow pointing from A to B. And then also notice that we put in this little cross across the arrow right over here. This is trying to show that of course, the arrow is pointing towards the more electronegative atom, and this little cross slash over here is sort of representing that this A is slightly more positively charged than B, which would have more electron density on it. So this is the arrow method. Let's look at an example of how we can use this with ammonia, or NH3. Okay, so first, drawing out the Lewis dot structure for ammonia, we have nitrogen singly bonded to 3 different hydrogen atoms, and then there is a non-bonding electron pair on the nitrogen. Each hydrogen has an electronegativity value of 2.1 according to the Pauling electronegativity scale. And then nitrogen's electronegativity value is 3.0. So this means that the nitrogen is more electronegative than the hydrogen atoms. We can show this with the arrow method by drawing the arrows pointing towards nitrogen from hydrogen and then putting the little plus sign on the ends of the hydrogen ends of those bonds. So that would be the method with the arrows. Now, which method to use and when, it really is very context dependent. You're going to see we're going to use the arrow method quite a bit in the next part of this lesson, but then other times later on in the course, I'll use the delta method pretty commonly. So that's the difference between a polar and a nonpolar covalent bond. Let's finish up the Chapter 9 lecture note outline on the next page and see what we're going to learn about next. So now that we know how to draw Lewis structures, we're going to learn about a theory called VSEPR theory, or VSEPR theory. VSEPR theory allows us to predict the shape of a molecule based on its Lewis dot structure that we draw. And we're going to learn how this theory works first on this last page in the lecture notes, just the basic ideas of it. And then we're going to learn how to actually do it in a separate video. So basically what this theory is, it's called VSEPR theory, and that stands for valence shell electron pair repulsion. This is an acronym where we have VSEPR. And the key word there is the electron pair repulsion, the EPR part. And what it suggests is that because electrons repel each other when they are around an atom, they will try to get as far away from each other as they possibly can. So the image of these balloons here gives a pretty good idea of what I'm talking about. That is, electrons themselves, when they're around an atom, want to get as far away from each other as possible to minimize the electron-electron repulsions that we would expect they would have, right? Electrons all are negatively charged, and like charges tend to repel each other. So valence shell electron pair repulsion theory states that when you have electrons, or pairs of electrons, around an atom, those pairs of electrons will get as far away from each other as possible to minimize their interactions. So imagine it like the balloons that I have shown here. So in this case where I have the two green balloons, two balloons, so this would represent one pair of electrons and another pair of electrons, will try to get as far away from each other as possible because of the space that they occupy. So if we tied two balloons together with an sort of around an atom here in the middle, the electrons around that atom would be on opposite sides of each other in this sort of linear arrangement. So we're going to see that's one of the predicted shapes, electronic geometries, I should say, in the VSEPR theory. Now, what happens if we put a third balloon in, like we have shown here? Now, because we have three balloons, the balloons themselves, the lobes of these balloons, have to get closer together than they were in this case, right? They're 180 degrees apart in the first case, but in this case, they're only 120 degrees apart if we look at the middle of each one. That's because there are three of them, and since they all take up space, there's less space available. And VSEPR theory says that electrons will behave a lot like this as well. If we have three pairs of electrons around an atom, they will tend to occupy this space, ideally where there's 120 degrees between them. Now, what happens if we have four balloons tied together with sort of an atom right in the middle of these balloons? Now, notice first of all that these four balloons are not all in the same plane as one another, right? We have the three balloons at the bottom, in this bottom plane, but then we have this fourth balloon sticking up above. Why didn't they all just go flat, sort of in the same plane as each other, like where they would be 90 degrees apart, like they do in this case? Well, that's because we have the third dimension available to us. And when we have that third dimension available to us, there's more space that we can use above or below the plane. So, in fact, we have angles here, if we think about it, right between this balloon and this balloon, that is a larger number than if they were 90 degrees apart. And it turns out to be about 109.5 degrees. So these we're going to learn are the three electron geometries or electronic geometries that we see predicted by VSEPR theory when we have two things around an atom, three things around an atom, or four things around the atom. So this is what VSEPR theory does. It thinks about a molecule as consisting really of two main parts. So let's look at an example. Let's go back to ammonia, which is NH3. This is the Lewis dot structure we will get for ammonia when we draw it out. And what VSEPR theory does is it looks at this, trying to predict the shape of ammonia based on this Lewis structure. And it does so by thinking about this as two parts. We have nitrogen in the middle, so we'll call that the central atom. And then attached to that central atom, we have terminal atoms, the hydrogen atoms. So we have central atoms and we have terminal atoms within molecules. And then to predict the shape, we think about how many things are connected to this central atom. And notice here, I have two types of things connected to nitrogen. I have the hydrogen atoms that I put in green squares. There's three of them. And then we have also this other thing on the central atom, which is this non-bonding electron pair. If we add up all the things around that central nitrogen, we see there are three green squares or hydrogen atoms, and then there's this one non-bonding pair. So a total of four things. VSEPR theory predicts the shape of this based on the number of things attached to that central atom. So what we're going to do in VSEPR theory is draw Lewis structures and then count up the number of things attached to central atoms, things being non-bonding electron pairs and terminal atoms. When we come up with the number of things, then we will be able to determine what the shape of that Lewis structure would be like in 3 dimensions. So let's write this down. VSEPR theory states that the best geometry for a molecule is based on two factors. The first factor being the number of terminal atoms connected to a central atom. So if we draw the Lewis structure, we can count up the number of terminal atoms, and this is one factor that we need to consider. Now, there's another factor we have to think about. Not all of the electrons around an atom are going to be bonding. Sometimes we have non-bonding pairs of electrons, and that's the second factor that will determine the shape in VSEPR theory, is that the number of non-bonding electron pairs also comes into account. So what we're going to end up doing is counting the number of terminal atoms connected to a central atom, and we're going to add into that the number of non-bonding electron pairs. These are also called lone pair electrons. So we're going to add these two things together and come up with a number, and based on that number, we will come up with a description of the shape and sort of a picture of the arrangement of the atoms. And I'm going to summarize that in this table I have down here below. So in the VSEPR theory, we're going to add up the number of terminal atoms and the lone pairs on a central atom, and we will get different combinations of these. If we add up the number of terminal atoms and the lone pairs, and we get the number 2, the arrangement of atoms we see in that case is like when we had two balloons tied to each other. We get a linear arrangement where the ideal bond angles are 180 degrees apart between these two things that I have shown here. Again, those can be atoms or lone pairs. They're 180 degrees apart because there are two of them. Now, another possibility we can get is when we have 3 things around a central atom. That's like 2 lone pairs and an atom, or 2 atoms and a lone pair, whatever. It adds up to 3. When we have this, we get a geometry we call trigonal planar. Trigonal planar. Now, the word trigonal refers to there being 3 things in the shape, and then planar refers to the fact that these are all in the same plane as each other. Another word for planar is flat. So they're coplanar or flat. And the bond angles here, the degrees, are 120 degrees because we have 3 things within the same plane. So by planar, let me draw a little sketch over here of what I mean. If we had X in the center and then the objects, they would all be in the same flat plane, like on a tabletop together. Now, so that's when we have 3 things. What about the next case, which is if we had 4 things around a central atom? I showed you a picture of this in the balloon image I showed earlier. When we have 4 things around a central atom, we get the third dimension arising into this shape. And this is what we call a tetrahedral geometry. And it looks like a pyramid, which I'm trying to show here in 3 dimensions. So we have these 3 things around each other in the same plane, but then that X is offset a little bit up from that plane. And then we have another object pointing up. Okay, and this is called tetrahedral or a pyramidalized geometry because it's like a pyramid. And the bond angles here are 109.5 degrees. This is called tetrahedral. So this is what VSEPR theory predicts as the 3 basic types of shapes that we will see. We can have 2 things around a central atom, 3 things around a central atom, or 4 things around the central atom. Now, because those things can be either terminal atoms or electron pairs, and in various combinations, we're going to learn in the next video lesson about the subcategories of these. So for instance, when we have 4 things around a central atom, we might have one of these things being a non-bonding electron pair, but the other things are atoms. We have a different name for that when one of those things is an electron pair versus all of them are atoms. Similarly, if we have 2 atoms and 2 lone pairs, we have a different name for that as well. So make sure we have a good descriptor for all of those combinations. That's what you're going to learn about in the next lesson. So with that, I will end this video. Thanks for watching. Please let me know if you have any questions. Take care.